along. So now I'm getting into section 2.6 here in Atkins, which is all about adiabatic changes. So thus far we've discussed either constant volume processes or constant pressure processes, which basically result in the case of constant volume, no work being done. In the case of constant pressure, there is work being done in addition. However, that work ends up being zero, right? dH ends up equaling heat at constant pressure. So now let's discuss adiabatic changes. And for adiabatic changes, we know dQ equals zero, so there's no heat exchange between system and surroundings when something is adiabatic. All right? And so that means if we are looking at, let's say, a temperature versus volume curve, now if we're changing the temperature and volume of something, the work done, okay, matters. And as you might also note, because temperature is changing on this scale, when something is adiabatic, it can't be isothermal, okay? So there has to be an accompanying temperature change, can't be isothermal. So there has to be an accompanying temperature change when something expands adiabatically, okay? And so it can be shown the following relationship. If I change the volume of something from VF to VI, okay, then there has to be a temperature change from TI to TF. And it's related to this relationship where TF equals TI times the ratio of VI over VF. And I know this kind of looks goofy the way that this constant is written. I just want to be consistent with the book. So that's what the book is showing, okay? And when we imagine moving down this line, changing temperature and volume, right? A good way to think of this is kind of like as a vector, right? That this is motion in two different dimensions on this space. There's motion in this direction at constant t, right? So if you move along this line, so u is a constant when the temperature doesn't change. But then now there's motion along this line at constant volume, where there is a change there, okay? And so number one, you know, u is constant. And number two, you notice that this says delta u equals CV delta t, because along this line right here, that's a constant volume line. So we can call up this equation for constant volume. Okay, so how does this all work out? How do we, so I want to derive, let's see what I have on the next slide. Yes, okay, so I've got plenty of space here to work. So now I want to work out so this is again another one of these scenarios. Let me rewrite that. And this scenario, reversible adiabatic expansion of an ideal gas. So we're adding lots and lots of qualifiers, right? We've already talked about reversible expansion. We know what that's all about, okay? So reversible expansion is PDV, right, where I have to actually integrate the P, okay? And adiabatic, we recognize adiabatic refers to the following: du equals dq plus dw. So because it's adiabatic, dq has to be 0. And thus, du equals dw. Okay? Well, what other relationships do we know? Well, I'm going to make a little inventory over here on this side. We know that dw equals negative p dv for reversible changes, for reversible expansion or compression. We also know when volume is being held constant, okay, du equals cv dt. Another relationship that we know that um equals 3/2 RT, but that doesn't really do anything for us because we don't see any volume dependence. So now what we can say, okay, I've got du equals dW. And by the way, this is another like pretty challenging derivation, so instructor assist, right? I wouldn't expect you to be able to just come up with this. So if we know du equals dW, then I can say, let's see, I lost my train of thought here. Oh, yes, okay. So then I can say CV dt equals negative PdV. So I got that by saying I know du is CV dt, and I know dW is negative PdV. So I write that down, okay? And we're dealing with an ideal gas. Oh, yeah, so another equation that I know is nRT over V, okay? And I'll go ahead and make that substitution. CV dt equals negative nRT over V dV. And now I'm cooking. And I'm cooking because, look, I'm interested in changes in temperature, dt, with changes in volume, dV, right, to get the slope of this line, okay? And there we go. I've got a dt and I've got a dV. So I know I'm on the right track. And what I'm going to now do is combine all like terms with all like terms and say CV dt divided by t equals negative nr divided by v dv. And so now what we can do, so this process I like to call divide and conquer. So we divided, and now we're going to conquer. And the way that we conquer this thing is by integrating both sides. So CV dt over t equals negative nr over v dv. So I integrate both sides with respect to their variables, okay? And so what I get, and so of course I'm integrating those right from, I'm just going to say I and F and I and F, and we recognize that this would be Ti to Tf, and this would be Vi to Vf, okay? So dt over t gives me natural log, right? And the constant Cv, we'll just assume that it's constant over this temperature range, okay? So putting this over here, we've got now Cv times natural log of Tf over Ti. And then now dV over V is also a natural log relationship. So I'm going to get negative nR times natural log Vf over natural log Vi. Okay. And then now I'm going to do a couple of log tricks. Okay. So I'm going to divide this over to this side and say that that's Cv over nR times natural log of Tf over Ti. I'm also going to do, so that was just algebra. I'm going to do a log trick here, and that negative sign I'm going to absorb into the natural log, which makes this ratio flip. So now that just becomes natural log of Vi over Vf. Okay, I'm going to call all of this stuff, right, lowercase c. Okay, and there's another log trick that I can do, and that log trick is when I have something in front of a natural log, I can raise it to the power in the log itself. So I can now say natural log of Tf over Ti raised to that constant c equals natural log of Vi over Vf. And I ran out of room. However, hopefully you can see, right, the way this is going to go. So if let's see here. Yep, so if I take E of both sides, then I'll get Tf over Ti equals Vi over Vf raised to that constant c. And then now the algebra, right, I'm not going to finish this because I don't want to write a bunch of sloppy stuff. But see if you can finish the algebra and arrive at that relationship from there. Okay? So let's see what I have on the next slide. Okay, so this relationship, this gives us this curve here. So this gives us a way of predicting what is the change in temperature when we have expansion of an adiabatic system. And so how, physically wrap your head around what's going on there, right? So imagine you have a gas and it's in a container, and that container is able to change volume. It's able to expand or compress, but that container is adiabatic. It's isolated. It doesn't allow the exchange of any heat. Okay? So what we would see as this adiabatic container is expanding, the gas inside has to cool down, right? You notice this relationship. So that's I and F, and this is I and F, initial and final. And so what's physically going on there, right? As the gas is expanding, it can't acquire heat from the surroundings, so it has to use its own heat to fuel that expansion. That's why the temperature decreases in the expansion, in the adiabatic expansion of a gas. Okay? So the same relationship that I'm talking about right here can be written in another way. Okay, keep note of how this goes. TF equals TI. If I multiply the constant through and set this up in kind of like a Boyle's law or a Charles law kind of a way, right? You can write this as, so this, I wrote that as PF and VF, but I think V and T is what I meant to write. Okay, so sorry about that. That should be T, and that should be T. So let's rewrite that. So that should be T final times V final. And I'm going to raise this, I'm going to put a new exponent in there, okay, that we're going to talk about now, equals TI. Yes. Sorry, I'm just checking to make sure I get this written correctly. Yes, equals TI times VI raised to this constant gamma. So I did a little bit of extra algebra here that you can follow through on the book if you want to see where it comes from. But this is basically another way of talking about this adiabatic expansion. Or like if we were writing this in like a Boyle's law, Charles law kind of way, we can say TV raised to some constant is a constant. Or in other words, T is proportional to 1 over V. I'm gonna erase that C and use the gamma to be consistent. That's a Greek letter gamma. So what this also means, T is proportional to 1 over V raised to this little gamma. So note, compare that to Boyle's law, which says T is just proportional to 1 over V. Okay, so now what we have here, this is what we call an adiabat, which you can see indicated by this blue line. And so this is giving it to you in terms of P, but we could also draft this up in terms of P. Okay, so I said T is proportional to V, T is proportional to V, but we could also, I think that's why I confused myself. We could also write this in terms if we were fixing the other variables, right? Isotherm, adiabat. Sorry that that's confusing. Okay. So, yes. So now what we can see on this three-dimensional scale here, just playing around with these adiabats and isotherms. So the isotherm is going at constant temperature, right? So you notice on this three-dimensional curve, it's just any one of these slices, right? Any one of these slices could be an isotherm, okay? But an adiabat, on the other hand, so those are probably going to get confusing to see. An adiabat, on the other hand, because it has this exponent right here, it's 1 over V raised to some power gamma, which now I'll talk about. Gamma is the ratio between CP and CV, okay? All right, so whatever CP and CV is, you can tell we would still have to plug in an equation for CV, an equation of R, and we're going to do that next, all right? This means that adiabats fall off steeper. They have a steeper slope, when you look at this at a two-dimensional graph, right? So you can see on this two-dimensional graph, the adiabat has a steeper P versus V relationship than the isotherm. And that's, again, because of these additional degrees of freedom that are required to be populated throughout this expansion or compression. And so depending on whether it's a monatomic gas, linear molecule, or nonlinear molecule, the adiabat may fall off even steeper depending on what this fraction gamma is. Okay? So sorry this was confusing with the P's and the T's and the T's and the V's, right? It's just like using our gas laws the same way we did before. If we know we can fix one, we can talk about the relationships of the other, okay? But it's important to note adiabats cannot be isothermal, right? You notice on this three-dimensional graph, it is changing temperature, okay? So